Resonance. This is a very important concept. It was put forward by Heisenberg. Heisenberg. So, according to this resonance concept, whenever a single Lewis structure cannot describe all the properties of a molecule, and therefore we need a number of structures with the similar energy positions of nuclei. Is required. It means a molecule cannot be described by a single Lewis structure. It is described by the number of structures with similar energy levels. And they involve bonding and non-bonding electrons. A number of structures with the similar energy positions of nuclei. For example, we already discussed one molecule can be represented by more than one structure, and those structures have similar energies. So it means, as I already explained, one person cannot be explained by a single representation. So he has got the multifaceted personality, something like that. So a molecule cannot be expressed or described by a single Lewis structure. It needs multiple structures, but they have closer energy levels. So if it is a situation, there arises resonance. So what is resonance? When a molecule cannot be expressed by a single Lewis structure, and that can be explained or expressed by more than one structure, and those structures have similar energy levels, there arises resonance. And in that case, you have bonding electrons and non-bonding electrons. Be means bonding electrons. NBE non-bonding electrons. And this can also be called a lone pair of electrons also. Like in the case of we discussed in ammonia, we have H, H, H. So there is a lone pair of electrons. So this is called LP or non-bonding. They don't involve in bonding direct. So when you talk about resonance, it was proposed by Heisenberg, and according to resonance concept, a molecule cannot be expressed by or represented by a single Lewis structure. It needs more than one structure, and they vary in very close energy level only. So it means they have very close energy levels, similar energy levels in the nuclei, and they have bond electrons and non-bonding electrons. And it is because of the position, it may have different forms. And such forms, these structures are called canonical forms. These are all hypothetical forms. Imaginary, you can say. And all these structures can be represented by a single structure, and that is called a resonance hybrid. So the mix of all these structures can be called as one structure called resonance structure or resonance hybrid. For example, let me explain. Now let us consider ozone. Take down ozone. Huh? Okay, right. So, so let me consider the ozone. Ozone has which one you want? Where canonical forms means the individual structures. I'll explain. Now, listen, let me consider this ozone. This ozone can be represented by simply one structure, but according to Lewis structure, we can draw like this. So, this we have already undergone a practice. You can find bonded electrons and non bonding electrons. Okay. So, here the bond length is 12154 meter, being a double bond. As I already told you, when it is a multiple bond, the bond length is less. And what about this? This is a single bond. This is 148 picometer. Now this undergoes a resonance. So the resonance is represented by a double-headed arrow. Now instead of representing the double bond here, we can represent the double bond here also. So how it happens? For example, see that is this one will come here and this one can go here. Now you see oxygen is there. Now it has become single bond and a pair of electron is shifted. So 2, 4, 6. And this becomes double bond. Are you able to follow? So this is possible because of the transfer of these pi electrons or pair of electrons. So this becomes 2 only. Now you can find that this is double bond and its bond length is 121 picometer. In this case, this becomes single bond, so 148 picometer. So likewise, this kind of transfer of electrons that lead to various forms, in this case, two forms, right? So they are called canonical forms. Do you understand now? Or it can be called resonating structures. Okay? And these canonical forms can be represented by a single structure. This is an equivalent structure as a resonating hybrid. How? So this electron can be transferred here and here. So this can be represented like this. So 2, O, and you can put like this. So this involves in transfer. Do you understand this? So this kind of representation, and this is called resonance hybrid. See, you've got two rooms here. The small kids, they will be playing here and here and here and here. So likewise, they keep on moving. So when their mom were in search of their children, they will be finding in both the places because they will be simply moving here and there. So likewise, they are the pair of electrons that can be moving here and there. So that we come to a conclusion that these electrons can be either here or there. So let us put it out like this, and they represent the resonance hybrid. We understand now? There. Now let us move to the further one. What are the rules for writing resonating structures? Rules for writing resonating structures. So the canonical forms or the contributing structures or the resonating structures, so they contribute towards the resonance that we know, provided they obey the following rules. What are those rules? Rule number one. In all the contributing structures, the position of atoms should be same, remain same. So the position of atoms should not be changed. The basic structures should not be changed. So the position of atoms remains same. I will highlight this. For example, even though the ozone has got two canonical forms, the position of oxygen atom has not varied. Do you understand? Only the pi electrons are getting transferred here and there. Okay. So the position of atoms remains same so that the basic structure is not affected. And here the position of electrons, they differ. It may travel here and there. Okay. The position of electrons. Then the number of unpaired electrons, number of unpaired electrons, the number of unpaired electrons must be same in the contributing structures. For example, a molecule can be represented by more than one structure. So you can call it that is a resonating structure 1, resonating structure 2, resonating structure 3. So the resonance is represented by a double-headed arrow. In all these cases, the structure remains, the basic structure, the position of atom remains. Only the electrons are allowed to transfer here and there. But the number of paired electrons will be remaining same. Are you able to follow? Next. The energy of contributing structures should remain same. So energy of contributing structures, that is these canonical forms, remains same. Are you able to follow? Nearly same. Now let us talk about, I was using this term called resonating resonance hybrid. This is called resonance hybrid. So when a structure can be represented, when a molecule can be represented by more than one structure, but it has to be identified as a single entity. Even though, as I already told you, Prisha can be represented in various ways like daughter, student, citizen of India, okay, sister, okay, elder sister, younger sister. Likewise, the relationship may vary, but the person is one, right? So in this case, we have to represent, and that is why we give some school ID, student ID. That is called the resonance hybrid. So by citing that, we are able to represent the different aspects of what a particular person by a single identity. Like in the case of when you say Aadhaar card, it represents all. Where are you from? How old are you? Okay, so all the details can be gripped, so likewise. So this is a kind of what a general representation. So this is known as resonance hybrid. Okay, so this resonance hybrid, let us talk about the stability of resonance hybrid. Stability of resonance hybrid. Both of you should stay in camera. Next. See, that is, we want to have this most stable hybrid. So, in the most stable hybrid form, in order to get that, we had to follow the rules. Rule number one. Are you there? Where is Prisha? Gone. Okay, so stay on camera. Hmm. Right. So, the non-polar molecules are always more stable. Take down. Non-polar molecules are always more stable compared to polar molecules, that is, charged molecules. Second, canonical form having more than, that is, a more number of covalent bonds are stable. So, more number of covalent bonds means they are stable. Stability increases. Third one, canonical form having negative charge on electronegative atom, on electronegative atom, and the positive charge on electropositive atom. So they have better stability. So if a canonical form have more negative charge on the electronegative atom, more positive charge on the electropositive atom, that form is more stable. So these are the three important rules about the stability of resonance hybrid. Then resonance energy. The difference in the energy of the resonance hybrid and the most stable contributing structure is called resonance energy. So what is energy? Resonance energy, the difference in energy of resonance hybrid and that of most stable contributing structure or canonical forms. Okay, it means, for example, let me say that is you've got a molecule and this is represented by M1, M2, M3. So these are various representations. So you can call it canonical forms, canonical forms. And the most stable is marked here as M3. So all these three can be represented by MR, the resonance hybrid. So the energy of this resonance hybrid, MR, minus the most stable, that is energy of M3 with asterisk, most energy stable, is equal to the delta E of resonance energy, and that is known as resonance energy. I hope now you should be able to understand this. Okay, clear? So the difference in the energy of resonance hybrid, this is the resonance hybrid, and the most stable. So this is the most stable canonical form. So the difference between these two forms, the energies of these two forms, is called resonance energy. That's it. Okay. Then now let us discuss how the resonance occur in some organic molecules. Let us consider carbon dioxide. So resonance in hmm, E resonance hybrid, energy of resonance hybrid. I simply put a resonance and hybrid energy. So resonance, the energy possessed by the resonance hybrid. This MR is the resonance hybrid. Just I am putting some symbol minus, and among these canonical forms, M3 is more stable. So you have to consider the most stable canonical form energy. So the difference between them is called resonance energy. That's all. Hmm? Hmm. Resonance hybrid has energy. Yeah, it has got more energy. More energy. Next. The resonance in, take down, inorganic molecules. The resonance in inorganic molecules. Let me consider carbon dioxide, CO2. So C, you can put a double bond on both sides according to Lewis structure. So we have got this one. I think we already practiced this. So this undergoes now the bond can come over here. You have got two pairs of electron here and here two double bonds. Are you able to follow? Two double bonds. And this is a double bond. Now what happens is it can become minus by transferring the electron you can have here. Okay. So it means, yeah, it becomes a triple bond. Okay. So it becomes, take down O triple bond C, and then minus O, and this becomes double bond, and it has lost one electron, so it becomes plus. It has gained electron, so it has become minus. It means how the electrons has transferred. Listen to me carefully. For example, this will come over here. Okay. right? So when it goes like this, and naturally what happens? It has lost one electron. Oxygen has lost one electron, so it becomes plus. And this oxygen has gained electron, so minus. And this has become double bond. Okay. Hmm. 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 Yeah, that is a 2, 4, 6. And what about this? 1, 2, 3. So it means, how about the oxygen? How many electrons are there in oxygen? Usually 6. And that is a terrible. So it means that 6 plus 2, 8. So here it has got already these, not this one. I must put 2, 2, 2. Only the bond is paired here. So 2, 4, 5, 6, 7. So one excess, so minus. And here 2, 4, and here 2, 4, 5 only. So one less. And what about carbon? 1, 2, 3, 4. So it is neutral, right? So what about here? How many electrons? 2, 4, 3, 7 electrons. Okay. So one electron excess, so it attains minus. What about this? 2, 4, 5. So only 5 electrons, so one electron lost, so it has become plus. And here it maintains 4 electrons. Okay, right? Now the same can undergo a resonance like this also on the reverse side. So it means the triple bond can go here also. So from here to here. So C triple bond, and here you can put 2, 4, and here that is O with the 2. So this becomes plus and this becomes minus. Do you understand this? So now you counted how many electrons are there? 2 plus 4 plus 1, 5 electrons. So one electron is missing. So plus. Here 2, 4, 4 plus 3 is 7. So 7 electrons are there. So it becomes minus. And according to carbon, it has got 4 electrons. So it remains neutral, right? So likewise, we can build up nitrate anion. Take down nitrate ion, that is NO3 minus. How you can draw nitrogen? Okay, and how many electrons for nitrogen? 5. So we had to account for 5 electrons. So a pair of electron is donated to oxygen. So 2 over. And here involves double bond. So another 2 and one single bond. Okay. Now we can fill up with the oxygen. And here 2, 4, 6. And here 2, 4, 6. Additionally, one electron. So that is why it becomes minus. Okay. And that's why we call it NO3 minus, right? So what is this? Nitrate. And a harm. And what about this? 2, 4, 6. Okay. Now you can count the electrons also here. How many electrons are there for oxygen? 2, 4, 6. Okay. So 6 electrons. And the 2 electrons are donated. Okay. A pair of electron is donated from nitrogen. And what about this oxygen? 2, 4, 6 electron. Okay, what about this electron? Oxygen, 2, 4, 6 plus 1, 7 electron. So that is why it attains negative charge. Do you understand? Okay. So can you draw the resonance structure? So you should practice it properly. So instead of developing a coordinate bond with this oxygen, it can develop the coordinate bond with the top oxygen. Okay, can you draw? So N, let us put O. Now 2, 4, 6. And here you can maintain the same. Okay, double bond O. So 2, 4, 6 plus 1, 7. And here, that is, you have single bond O. Okay. So it means it will not have minus, it will have minus here. Because 2, 4, 6 1. Strike out this. So 2, 4, 6 plus 1, 7. So let us count how many electrons? 2, 4, 6 plus 1, 7 electrons. So it becomes minus. What about this 2, 4, 6 electron? And the donated electrons are here. This is the donated electrons. A pair of electrons donated from nitrogen. And here 2, 4, 6. So 6 electrons. That's all. Okay. Now can you shift the covalent bond here and draw? Try. That is N. Now coordinate bond is here. So 2, 4, 6. And here you have the O. Okay. So you can draw, you can shift either this or that. You can put double bond as here and single bond here. So O. So what about this oxygen? 2, 4, 6. And here 2, 4, 6 plus 1, 7. So it means here 2, 4, 6 electron stable. And here it becomes minus. Why minus? Because 2, 4, 6 plus 1, 7 electron. And here 2, 4, 6. And here 2 electrons are donated, right? Okay. Shall we try carbonate ion like this? So these are all very important questions. Please practice. Let us move ahead with carbonate anion. Carbonate ion. Shall we stay on camera? Carbonate. CO3, 2 minus. Now carbonate, the central atom is carbon and you've got the double bond O, O, O. So I said 2 minus. So it means both the oxygens have minus. Now can you propose the electron dot structure for this? Can you tell me here for double bonded O? Okay. Here, tell me 2, 4, 6 plus 1, 7. And here 2, 4, 6 plus 1. So you have 7 electrons here, 7 electrons here, and here 6 electrons. And what about carbon? 4 electrons. Okay, right? Now it is doubly bound. Now what you do is shift this double bond to the top, and you can draw one structure. Okay, and shift the double bond to the bottom. So can you draw two more structures? Try resonance. You can put C double bond O at the top, and here O and O. And the next structure can be drawn like this. C, put double bond O at the bottom and O here, then O. So you've got the double bond means the two pairs of electron. And here also double bond means two pairs of electron. And single bond O minus, O minus. So here also O minus, O minus. So now 2, 4, 6 plus 1, 7. 2, 4, 6 plus 1, 7. Right? So 2, 4, 6 plus 1, 7. 2, 4, 6 plus 1, 7. Okay? So you can indicate. So they are the resonating structures are also called contributing structures or canonical forms. Okay? Now let us study some useful applications of this resonance concept. Okay, take them. Applications. The important applications of resonance concept, resonance are one. First one, it is very useful to study or to calculate interionic distance. We can calculate interionic distance. Second, and thereby we can study the partial ionic behavior. Okay, partial ionic character of bonds. Interionic distance. We can calculate the so that is a cation and anion, so the interionic distance can be calculated. Second, partial ionic character of bonds can be analyzed. And based on that, we can calculate the energy of the molecule also. And we can explain the mechanism of several chemical reactions. And this explains the existence of odd electron bonds also. And this also helps, we can calculate with the help of this resonance energy, we can calculate the electronegativity, that is the relative electronegativity. So the relative electronegativity can be determined by using this formula 0.208 into the whole square root of resonance energy, where ER is equal to resonance energy. And 0.28 is the factor. So it means what? When you find that the resonance energy is high, it indicates the relative electronegativity. That is, it is more. So with the increase of resonance energy, you can say the electronegativity also increases. Do you understand? And before plunging into the next concept, that is a valency bond approach, that is valency shell pair repulsion theory, I would like to discuss one important problem here. Okay, take it down. All chlorine oxygen bond distance in ClO4 minus. What is this ClO4? Yesterday we discussed. Please refer perchlorate. Very good. So, what are the four types of oxy acids of chlorine? Okay, okay, very good. So, the relevant anion can be called perchlorate anion. Okay. So, what is the anion of a chlorous acid? Can you tell me? So first you tell me first, you know HCl, okay? What about the oxychlorides? That is HClO. Next, next, Next. Okay. So what do you call this one? Hydrochloric acid. Okay. And what about this? Hypochlorous acid. What is HClO? Hypochlorous acid. What is this one? Okay. So this is generally hydrochloric acid, chloric acid, and its relevant salt can be called chloride, right? For example, Cl minus means chloride. Okay. And what about this one? Hypochlorous acid. Chlorous acid. And what is the relevant salt? ClO4 minus. Sorry, ClO minus. What do you call this one? Hypochlorous, and which is anion. No, no, no. It is called hypochlorite. Take down. Hypochlorite. RITE. Okay. And what about this? Chlorous acid. OUS acid. And this one ClO2 minus. No, simply chloride. Okay. This is chloride, Cl minus. This is ClO2 minus means chloride. Do you understand? So what is potassium chloride formula? Potassium chloride. Very good. And potassium, ferric chlorate. I want ferric chlorate. Can you tell me? Ferric means Fe3 plus. Chlorate means HClO3. So you can leave this one. So ClO3 minus, right? Okay. So FeClO3 thrice. Are you able to follow? Okay. And how many hydroxyl atoms groups are there in HCl? No hydroxy, right? And what? How many hydroxyl groups are in HClO? No hydroxy. And what about this? One hydroxy. Here, two hydroxy. Here, three hydroxy. Do you understand? Okay. And how many coordinate bonds are available in the last one? Perchlorate. This is perchloric acid. And remove the H, then you have got ClO4 minus. What do you call it? Perchlorate. What is the formula of sodium perchlorate? That's all. NaClO4 minus. Okay. You got this point? Okay, so we are talking about this chlorate only. I mean perchlorate only. Perchlorate. Okay. So this perchlorate, now listen to me. All the chlorine oxygen bond distance in perchlorate, that is ClO4 minus, are found to be 144 picometer. Picometer means what? 144 into 10 power minus 12 meter. Justify your answer. Shall we try? Now listen, I'll explain with the first structure. Now, what I already told you, that is you have got Cl, okay? Now listen to me. In this case, you have a double bond O and one OH is there. So one O and two double bond O like this. And here, now can you put the dot? What about this oxygen? How many electrons? 2, 4, 6. Okay. And this is minus. And what about this? 2, 4, and you've got 2, 6. Here 2, 4, 6. Then what about this? 2, 4, 6 plus 1, 7. And that is why you got minus charge. You understand this? So this is the structure of what the chlorate ClO4 minus ion. Okay. Now here the O minus can go here, can go here, can go here. Likewise, it can form various structures. Shall we try various canonical forms for this? First, we will go here, here, here. Do it. C single bond O dot 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 minus. Okay. And here double bond O. And here also double bond O. And here also double bond O. Finished. And you can put dot 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 dot. And here dot dot. Done. Then next one. What is that? Let us push the single bond O here. So C single bond O. Now the remaining will be double bond O. Okay. Now let us fix the electron dot. This is minus means dot 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 dot. So minus here. Sorry, Cl. Then dot dot here 2 and then 2. Here 2 and 2. Here 2 and 2. Okay. And again that is it can travel here. Okay. So C put double bond O and bond O here. So dot 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 minus and here double bond O, double bond O, dot dot dot. Got it? Okay. So this is the way you have to practice. Now, so the probable structure, you can combine all these structures into one. What is called that one? Resonance structure, right? So let us try to arrive at the resonance hybrid. So like Cl, okay, and put O on all sides. Symbol simply O. And put the dotted line. It means they are traveling in all oxygen. So this represents what? The resonance hybrid. Are you able to follow? That is, it indicates that they are traveling here and like in the case of benzene, there is a delocalization. So this represents the delocalization of pair of electrons. Okay. And that is why all the ClO bonds are equidistant and they have 144 picometer. Likewise, you can establish. Is it clear now? Yeah, they have the resonance structure, and that is why they have got the equal bond length in all ClO bond. So this is the way you have to explain. If it is asked in a 3 marks question, you have to draw and explain using the structures. Okay, right? Now let us move to the next concepts. Okay, so meanwhile, let me ask you some simple questions based on whatever concept I have discussed. Get ready for the quiz. Okay. In resonance structures, there is a bonded electron and there is no non-bonding electron. Is it true or false? False. It has both bonded electron and non-bonded. Non-bonding electron can also be called a dash. What is that? Lone pair of electrons. Why it is called lone pair of electrons? Because it doesn't involve in the bond. For example, let me consider chlorine. So even nitrogen also, you have got nitrogen 2s2, 2p3 like this. Okay, 1, 2, 3, and this is kept alone. So that is why it is lone pair of electrons. Okay, whereas they are involved in bonding, covalent bonding with the hydrogen, so that you are able to get NH3. Right. Next one. Who proposed this resonance structure? Heisenberg. And how many resonating structures is possible in ozone? Two. And what do you call this one? Resonance hybrid. What is the other name for the contributing structures? Canonical forms. What do you call it? Canonical forms means imaginary structure, hypothetical structures, or you can call it a resonating structure. Then, when we talk about the stability, that is, with the increase of number of covalent bonds, what happens to the stability of resonance hybrid? Increases. Then, what is resonance energy? Most stable canonical forms energy. Okay. Now, um, okay. Then, here, how many electrons are involved in the C triple bond O on oxygen? Why? 4. So it means originally oxygen should have how many electrons according to the valency? 6. Now it has got 7, and that is why it has got minus. Okay, good. And how many resonating structures are possible in the case of nitrate anion? 3. 1, 2, 3. Okay. So can you draw the resonating structure, that is resonance hybrid for nitrate? Show me. Resonating structure for nitrate anion. What you are supposed to do, very simple: put nitrogen at the center, and you have got a single bonded oxygen, and put dot 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 on all sides. Okay, it means they are delocalized. Okay, it is traveling. So everywhere it is traveling. So you can put simply dot dot dot. One bond with extra dot dot dot. Okay, then uh, what is the relationship between what is the ratio between the relative? Yes, it's correct. Put one bond, and put dotted line on each bond. Dotted line. You are not put the dotted line on all sides. Risha is correct, but shall we? Have we put the dotted line? Okay, right, correct. Both of you correct. Right. Now, what are the applications of this resonance energy? There are six important points. Okay. So, can you tell me sharply? One is we can calculate. Second, can be studied. Third, the energy of the molecule can be studied. Fourth one, the mechanism can be explained based on resonance. And fifth one, there is an existence of, yeah, that is established. Now, can you tell me the ratio between the electronegativity and the square root of resonance energy is equal to dash? 0.208. That's it. Okay. Next. And we were discussing towards the end of this concept that the CLO bond, it has got the bond length of 144 into 10 power minus 12 meter. Even though it has got CLO, 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 likewise four bonds, all four bonds are equal. But when you look at the structure, you know very well that you have got three double bond O and one single bond, correct? You know already the single bond O and double bond O, there will be a difference in the bond length. Do you agree with me? Okay. Which is shorter, single bond or double bond? Double bond is, so if it is the case, there are three kinds of the bond length and one is different. But when it is experimental results show that it has got all equal, that is 154. Why? That is the question. So you have to explain and arrive at that it has established the resonance hybrid like this. Okay, got it? Right.